So, this presentation we are going to see microwave heating or microwave processing. So, in the case of OMI heating, we saw it is a volumetric heating, the both the liquid and solid, if they have the same electrical conductivity, they can heat together rapidly and you can able to minimize the temperature distribution. Microwave heating also an electrical based technology, and you use a similar concept volumetric heating, except the mechanism of heating is probably going to be different. So, when you apply microwave, the food absorbs the microwave, and that increases the temperature of the food, and it is going to destroy the microorganism and preserve the food. So, basically it is a thermal processing, time and temperature as the primary thing. Now, the non-thermal effect of microwave, they are there, but they oftentimes they do not consider significant. If you look at microwave history, it is kind of very interesting. It is relatively younger technology compared to say OMIC or some of the other technologies. In around 1940s and 50s, there is a radar engineer by name Percy Spencer. He was kind of working on some defense related things, and he had a chocolate bar in his shirt, and kind of noticed when he went to the radar room, the chocolate become melted. He was curious what caused the melting, and then he realized that the exposure to the microwave melt the chocolate. Then he kind of conducted additional experiments, eventually led to the microwave. So, the early days of microwave ovens, even for the home use, they were big cabinets, maybe probably the size of that audio room in the back. So, they are very huge, and because all the electronics and other things there. But probably eventually in 50s and 60s in the US at least, microwave become more common household items, and so it became everybody start using microwave. However, when you look at the industrial application of microwave, particularly for pasteurization and commercial sterilization in the US, it took almost around 2000 or 2015 when the first microwave petition was approved, or FDA issued no objection, so that it became a commercial process. Again, the Food and Drug Administration, they do not issue a letter of no objection, just you provide data. They want you to provide the scientific reasons why some technology work, and then if there is a process deviation, how they can take care of some of those issues, and so on and so forth. So, that is where it takes a longer time for the industry to adapt the technology. So, if you look at the microwave, it is a wave. So, that means it has a wavelength, it has a frequency, and then if you combine those things together, the lambda is the wavelength and then f is the frequency, that is the speed of light. So, because microwave is essentially electromagnetic wave, speed of light is constant, is 3 into 10 power 8 meter per second. And the household microwave use certain frequency 2450 megahertz, and then 915 megahertz is what they use in the industrial microwave. Why 915, why not 2450? Because the lower frequency going to have higher penetration depth, because when the industrial environment, you may be processing samples maybe with multi layers, maybe a very thick sample, having a longer penetration of microwave enable you to process food much easier than shorter penetration depth. Because at home you are not going to cook big stack of material, you are going to heat only small portions. So, having a small depth is probably it's okay. So, this is kind of part of the electromagnetic spectrum, and you can probably pay attention to this, because later on when we do the radiation, you will also use the same spectrum. If you look at one end of the spectrum, you have the X-ray, gamma rays, and so on. So they kind of have certain properties, certain wavelength, and then certain frequency. The other end of the spectrum is your radio frequency wave and then microwave. You can see here the wavelength is 1 millimeter, 1 centimeter, 10 centimeter, and so on. So as you increase here, the wavelength increases, but the frequency in this side is decreases. So it kind of goes in the opposite directions. So this is kind of where the microwave is used. Whereas if you look at here, this is the visible spectrum. One end of the visible spectrum is your UV. The other end of the visible spectrum is your IR, infrared radiation, all those things. So these are all kind of part of the same electromagnetic spectrum, which kind of used for the various food applications. And this just a slide just shows that what are the different frequencies adapted for microwave and OMI heating for various food processing applications. Now, what are the benefits of microwave processing? It's a volumetric. So that means whether you have a small particle or a big particle, you can able to heat them together. You can reduce the processing time. Now, when you do heat transfer with heat exchanger, you are heating a product, the material is hot, and then when you, it's kind of difficult to turn off the heat immediately and bring the product to cool down. Whereas with the microwave, you can turn it on, it's heat. When you turn it off, there's no microwave delivered, so it's going to cut off that heating, so you can able to distribute that temperature much more. And then you can also allow them to deposit that microwave in a particular shape and size. It's much more energy efficient. It can be combined with energy sources and chemicals. Now, even though microwave has the promise of what they call volumetric heating, we will see later on there is going to be uneven heating. So again, there are properties of the food material called dielectric properties, that different food substances have different dielectric properties that result in uneven heating. Again, understanding that will help you to prepare your microwavable food and frozen meals and so on and so forth. This is a simple concept to illustrate microwave processing. So when you apply microwave, this is part of the electromagnetic spectrum. So think about a simple torchlight. You take a torchlight on, shine on the surface, the light is going to apply it all over the surface. The same way, within the microwave, you have a magnetron which generates the microwave, and then you have a waveguide which transfer the wave into a chamber, and then it's going to distribute. And then you can have a chamber design in such a way that that wave is kind of reflected different ports and then focus on your sample. So the sample is going to absorb microwave, and then how does microwave heat the food? The simple answer is most of the food substances have water, and water basically trying to follow the microwave. So microwave, I mentioned 915 megahertz or 2450 megahertz. So it's like so much frequency. Hertz is 1 over second, so it's 10 power 6 per second. So it's much more rapidly moving up and down. The water molecules try to follow that frequency. It also try to move up and down. When they move up and down, they collide with the adjacent molecules, and when they do that, that's create a friction, and that result in temperature increase. So that's how the microwave can create that. The same way, you also have salt like sodium chloride, for example, sodium and chloride ion. they are also similar to respond to the microwave, and then you can also get some heating happen during that microwave processing as well. So, from an industrial scale, like we said, home microwave have been there long time in the US, probably from 60s and 70s, and now all over the world, many households have microwave at home. So it's kind of people kind of mostly use them for preparing, heating meals and things like that. But the industrial application for microwave in the US is very slow to adapt, because there are non-uniformity in heating, and the scientists have difficulty in kind of able to demonstrate that. So, there has been some work done at Washington State University, where they adapted what they call microwave assisted thermal sterilization process. So, what it is imagine you have some soup or you have some material, and then you are going to package them in a polymeric pouch, so that they are going to be sent through a certain mechanism. So, here you have a product is going to be heated to certain uniform temperature. So, maybe let us say you maintaining at 50 Celsius or 60 Celsius, you are going to maintain that, and then you are going to apply microwave in a particular zone. So, when you condition everything at the same uniform temperature, the electrical properties like the dielectric properties going to be in the same temperature. So, that means the temperature increase is going to be much more uniform, and then it goes through a cooling section, and then the product comes out after this. So, in this microwave zone, what they are also doing is, in addition to exposing the product to the microwave, you also have, you can probably see in this picture, the product is going through a zone which is filled with water. So, in other words, the microwave is delivered to the water, and then in turn it goes into the product. So, there's going to be two type of heat transfer happening. One, the product receive microwave, and then you are going to have a volumetric heating. The second, the water where the product is suspended, it receives some heat treatment through microwave, and that raises the temperature, and that heat also going to be transferred into the product. So, that means let us imagine this is your treatment chamber, this is your pouch, and then this is your water. You are going to send microwave here, it is going to heat. You are going to send microwave to the water, it is going to heat, and then this heat in turn heat the water. So, in other words, they are kind of trying to provide as much opportunity for the product to receive the heat from microwave as well as the surrounding water, so that any non-uniformity in temperature can be reduced, so that you have much more uniform temperature. Because ultimately, remember, in any of the processing methods, you have to demonstrate what is the uniformity of your treatment, how that will help to control the inactivation of microorganisms. So, that is the principle, and in the previously they did not have this concept. So, they were always going to have, in the absence of, for example, the water, you are only heating the product. That means you are going to have a non-uniformity. So, as a result, the FDA always come back, your heating treatment is non-uniform, so it is not acceptable. So, by adding some water in the system, they kind of try to make it much more uniformity. Concept wise, you have a power generator which generates the microwave, and then you are going to deliver through the waveguide, and then this is the treatment chamber. So, the treatment chamber is like, imagine you have a large water bath, inside which you have a conveyor belt, and in the conveyor belt you have these pouches kind of moving through. So, that way the microwave is delivered to both water and the treatment of the pouches, and thereby you can have much more uniform heat treatment. So, this is called MATS. So, this technology probably approved for industrial use around 2010 or 2012 time frame from Washington State University. Now, this is a batch process because you are processing everything in batch, because you have pouches where you are processing the samples. There is also another parallel development where they have a continuous microwave processing. So, imagine you have the same soup, but instead of packaging the soup, you are kind of pumping the soup, and then you are going to send to a treatment chamber, and this is your waveguide where the treatment is going to occur. So, in this example, your soup may be flowing here, and then the microwave may be applied here. So, that the microwave is applied, and then once you have that, you are going to have a whole tube, and then you have a cooling section, and then you have a aseptic packaging, and so on. So, it is a continuous method of processing. So, any pumpable product like pasta, tomato, sauces and things like that can be processed. Now, this method is commercialized by NC State University. So, for example, they commercialized this for some sweet potato puree, again about 2010-2015 time frame. So, in either case, you have to look at the uniformity of the temperature distribution during microwave processing. This is an example for one of the simulations. You can see that as you pass through microwave, the center portions here heat much more reddish, that means they are hot, whereas the blue or green, they are at a lower temperature. So, you can see they kind of try to visualize the non-uniformity of heating, and then they relate back to that the food safety. So, whenever you look at the new processing methods, you cannot just work in microbiology alone or engineering alone. The microbiology and engineering need to work with each other so that you have a safe product. So, this is just a continuous microwave processing, another schematic. So, you have microwave energy is being delivered to the product, and then the cold product in it's heated, and then the hot product is going through the section. Now, when the microwave sterilization pads or now they call that MATS, microwave assisted thermal sterilization, that is the one initially they were aiming for. Once they commercially successful, then now they start using the same concept for pasteurization. Remember, pasteurization is a mild temperature, whereas sterilization is high temperature, much higher temperature. So, in the case of microwave assisted thermal sterilization, they may be achieving temperature in the range of 130-140 Celsius, whereas in the pasteurization they may be achieving temperature about 70 Celsius or 80 Celsius, so that they can achieve pasteurization. So, it is kind of the concept is kind of similar to thermal, except the heat treatment can occur with microwave delivery. So, they are trying to experiment with the ready to eat meal, heat sensitive viscosity products and things of that nature. So, as of now, microwave pasteurization is not widely practiced in the US. Part of the reason is, I think again, a lot of the industrial segments now adapting high pressure pasteurization. So, a lot of the commercial products pasteurized in the US, they either conventionally heat pasteurized or they start adapting more microwave, not microwave, the high pressure pasteurization. So, whereas microwave pasteurization is relatively a new processing technology. Now, normally when you look at temperature distribution, you kind of talked about the thermal diffusivity. So, that is defined by K rho Cp. So, your thermal conductivity, your density, and then your specific heat, these are all play important role. So, these properties also important in the case of microwave processing when there is no microwave applied. But what are the microwave related heating parameters? So, the microwave related heating parameters are they called the dielectric properties. So, microwave heat material in two ways, one with water, the second with the salt. So, water has basically dipolar and they try to follow the water molecules, the electric field, and they then agitate, and with agitation brings the friction that result in heat being generated. The same way electric fields like salt, sodium chloride, sodium and chloride ions also oscillate, and that produces heat as well. So, this is just to give you how the sodium and chloride kind of try to agitate and creates the friction, and then here the water molecules how they both have creates friction with the microwave field. So, those are all kind of reasons why it is there. The rate of energy generation per unit volume inside a microwave can be calculated using this relationship 2 pi, the frequency, the electric field, and then you have two parameters epsilon 0, epsilon double prime. So, epsilon double prime, epsilon 0 is the permittivity of a free space, epsilon double prime is the dielectric loss factor. So, we will talk about that in the next slide. So, dielectric loss factor is the ability of the material to absorb wave, how the material dissipate energy into heat. So, there are two parameters. So, I mentioned microwave is like a light waves. So, when you apply microwave, there are a couple of things possible to happen. One, the wave can shine on it and then it can be reflected back. The second, the wave can go inside the product and then it can dissipate within the product, or the wave can just pass through the product without anything. So, like for example, when you take a torchlight, you apply on the table, this table does not allow the passage of light, so it may reflect. Whereas, if you have maybe a glass with a blank in the bag, it is going to stay inside. Whereas, if you have a glass sheet, it allows the passage of light. The same way, food materials either reflect the microwave, like or some packaging material may reflect the microwave, or some food materials could absorb the microwave, or some materials may just transmit the microwave. So, there are different properties. So, that is what we call dielectric loss factor. So, it is kind of even here. So, you have an incident light either reflected, or it is going to be absorbed inside, or it is going to be transmitted. So, each property, each material have certain property, and you are going to characterize them, and then you are going to have certain value you calculate. So, in case of food material, you want the microwave to be absorbed, and then it is going to stay in the food material. So, once it stays in the food material, it is going to agitate the molecule, water molecules, and that produces heat. So, how much microwave absorbed, and then how much of that absorbed microwave is converted into heat. So, those are the things you need to pay attention to that. So, now we are introducing two concepts. One is the relative dielectric constant. So, the ability of the material to store microwave. So, in other words, you kind of shine the microwave on the food and it is going to be stored inside. So, that is your epsilon prime. Second, you have relative dielectric loss factor, ability of the material to absorb wave and then that is dissipated into heat. So, once it is absorbed, that is converted into heat. So, that is the factor, and you have the values given here for some different type of products, you ranging from epsilon single prime 74 to 1, and then epsilon double prime 21 to 0. So, and then you have a third parameter which is called tan delta, which is basically a ratio of the epsilon double prime over single prime, and it indicates how well microwave is converted into heat. So, that means you have to convert that into heat. So, let us kind of look at here water. Water has value of 8 and then epsilon double prime 10. Ice has a value of 3 instead of 80, the same when you cool down become ice, it is significantly 3. So, that means the ability of the material to store electrical energy. So, ice has less ability to store compared to water. Water has more ability to store microwave. The second is water has a double prime of 10. So, that means it is going to dissipate much more effectively into heat, whereas ice has 0.003. So, in other words, if you are cooking for example, just a vegetable or some product which is in the refrigeration temperature, you are going to heat much more uniformly when you have just water there. On the other hand, you try to take a frozen product and then you try to do the microwave, would you expect the frozen product to reach cooking immediately? It is not. You go through some type of freezing and thawing cycles. The reason is what you are trying to do is when you have just room temperature water, let us say this is 25 degrees Celsius, you are going to heat, there is going to be some slight temperature increase. So, you cook the food. Whereas, in the case of freezing, let us say this is 0 Celsius, you are going to be say minus 20 C, you are going to have some type of above freezing, you try to bring the temperature above freezing, and it is going to be slow process, then it is going to rapidly increase the temperature. So, that is the reason the water and ice, they have different dielectric properties. While we are on the same topic, look at oil and the parameters, they are also similar to ice. So, in other words, if I have oil and water, water has much higher dielectric properties, whereas oil has much lower dielectric properties. So, that means they kind of behave like a more ice in terms of absorbing and generating heat with microwave. One key difference between oil and water is the specific heat. The specific heat of oil is, what is the value? Is generally low, whereas water it's about 4.1. So, that means it is much higher. Because of those difference in specific heat, you have to consider, in addition to the dielectric properties, you have to consider the specific heat of water. So, that when you consider overall heating rate of microwaves during oil versus water, you have to take that into consideration as well. The other thing you have to consider here is salt water. When you add salt, the dielectric property is going to decrease, the ability of the material to store the electric energy slightly decrease, but the ability to convert into heat is going to increase. So, in other words, again like Omi heating, adding salt probably help to improve the heating rate in certain ways. So, again you have to kind of study the dielectric properties of different materials when you are formulating microwave heating, so that you can able to adjust your heating rates during microwave heating processes. So, this just gives you the specific heat of water 4.1, whereas you have oil 1.67. So, in other words, water requires lot more energy 4.1 kilojoules, whereas oil requires less heat energy 1.67 kilojoules energy. So, the heating rates kind of they take a different pathway, even though the dielectric properties of oil is lower than the water. So, the other thing probably going to happen, remember when we talked about electrical conductivity, we talked about how the electrical conductivity and temperature they are coupled with each other. In other words, when you add certain temperature, it is going to increase the electrical conductivity, which in turn increase the heating rate and then increase the temperature. With the increasing temperature, you are going to increase the electrical conductivity and then so on and so forth. The same way, when you have a microwave at low temperature, when you shine the light on the microwave on the product, the absorption is going to be lower, but it is going to start heating. Then it is going to penetrate more into the product, it is going to heat up the product, then it is going to absorb more microwave and then it is going to heat generate. So, it is going to keep going, the temperature and the penetration of microwave going to increase. And what is going to happen is you may have different food materials have different absorption capabilities. So, that means they are going to heat in different ways within the microwave. So, that is the reason why, to avoid that non-uniform heating, in the case of Washington design, they just added water in the mix. So, that they are heating the pouches in the presence of water. So, you not only heat the product with microwave directly, but you are also trying to use the water as a supplemental heating, so that you maintain certain uniformity of the product. Attenuation factor, it is kind of the decrease in the power on intensity of microwave as it travels through a medium, and it is calculated by this complex equation. So, you have the epsilon prime then delta, and it kind of provides certain value. So, let us imagine you are a food process engineer working for a company which prepare microwavable foods. Then you have to study all these engineering properties related to microwave, characterize them, and then you kind of prepare your microwave foods properly. The another parameter is the power absorption. So, the power absorption is in the microwave. So, we talked about ice and water. Initially it is frozen. So, generally it does not able to penetrate much, but once you warm up, you can able to penetrate more in the product, and that generate more heat in the case of microwave, and this is kind of given by this relationship here. The other thing you need to consider, we primarily looked at microwave of food materials. Now, most of the food products packaged in microwavable containers, right, like you may have a polymeric film or things like that. So, polymeric films also going to have microwavable characteristics. So, that means some films going to reflect microwave, some films allow passage of microwave through them, or some films probably just totally transparent to microwave. So, you have to kind of use appropriate film in your package material, so that you can able to get proper things. Let us suppose you are preparing a TV dinner. So, what that means is, so for example, you may have some rice and some vegetables, and then you may have some type of sambar or soup type material all in the same package. Your rice may have certain microwave heating properties, your vegetables or meat may have certain heating property, your soup may have certain different heating property. So, if you have a film which allow the microwave to uniformly apply to all the three components of the tray, you are going to have maybe one is very hot, another may be slowly warming up, and so when the consumer receiving it, they may have a unpleasant experience because either they get heat damage, because it's very hot, it harm them, or they may have a not very lukewarm product, so they may not like it. So, how do they allow microwave uniformly heating is by properly select the films. So, you may be using film, let us say the microwave for rice takes more effort, they may allow more microwave to pass through the chamber where rice is there, whereas if your soup require less heat, then they have a different film which only release very little microwave to pass through. So, by selectively controlling the properties of the film, they can make sure that they may just say, okay, microwave this box for 5 minutes. So, at the end of the 5 minutes, all the three components going to be at the same temperature because of the design, so that the consumer going to enjoy the product, but they don't need to worry about all the complexities of how to design those things. That is the job of a food engineer or packaging person to come up with the right choices and so on. So, again microwave has a complex temperature distribution. So, shown here you have hot and you have cold and so on. That temperature distribution can be modeled using finite element finite difference methods shown here. So, again you can see that you have a heat diffusion component here, and then you have a heat generation due to microwave, and then this may be some evaporation component, and this is the energy input to the product. And then if you solve for the temperature field, you can find how much heat distribution, and then from there you can be able to establish the uniformity of treatment. So, in terms of critical process parameter, again microwave is a thermal process. So, we always talked about temperature and time is the primary process parameters. In addition to that, you also have shape, volume, surface area, packaging can play a role, and then the geometry of the design of your equipment can play a role, what frequency you are operating, whether or not you have a agitator in the system are going to play important role. When you are cooking foods with microwave, you can probably, because of the uneven heat, especially when you have high sugar content, you can have scalding effect, because maybe portion of the sugar is going to be get very warm, and that can result in mouth or tongue burn. And similarly, when you have a steam generation in a sealed product, you can generate heat with a lot of steam inside, and then you suddenly open, it can cause burn. So, that is something you have to pay attention to it. One of the things you need to pay attention is microwave and metals, they do not work with each other, because you can create a arcing. So, that means you kind of want to avoid those type of things in the microwave. And when you have styrofoam type of containers, they can probably melt, and again that is something you kind of want to avoid. The microwave, when first introduced in the 40s and 50s, people worried about the microwave safety, whether how affect human health. So, in 1968, Congress allowed the FDA to protect public safety, and then they were testing procedures. So, for example, our house we are using microwave, but those microwave do not expose to the humans, they are contained within the chamber, and they wanted to provide leak tests to make sure that there is no microwave leak out of the microwave containers and so on. The industrial application of microwave is pasteurization, sterilization. It's kind of already more practiced in the Europe, whereas in the US, the sterilization just commercially approved, but it's not widespread. It happened in 2010 time frame, so it's still evolving. Pasteurization research is more coming along. So, a company in North Carolina, they have been processing sweet potato puree with microwave processing. That is one of the applications. The other applications include some fish processing and things like that. So, it is kind of relatively limited applications there, but there is planning to have more application. Coincidentally, the Tata Corporation in the US, in India, have a partnership with the US company, and they are trying to bring in microwave processing to some processing food in Indian context. So, this is kind of provide some examples of microwave heated products, and you have some reading materials you may find useful. Now, we can go for some discussions.
Sir, that additives like salt, can it be used to increase the dielectric loss of low heating foods?
Right, sure. You can probably alter the heating properties of microwave, dielectric properties of microwave using salt, but similar to Omi heating, you have only so much salt you can add to the formulation. So, you have limitation from that point of view.
Okay. And means what is the main mechanism of microwave heating? Means the dielectric or the ionic conduction? Means which one?
So, most of the food contain water. So, it is a dielectric heating of water probably the predominant, because salt is relatively smaller portion.
Yes, yes.
Right.
Okay, sir. Thank you, sir.
So, in microwave heating, if we are heating spaghetti and meatballs, for example, how is it ensured that it is uniformly heated? Because spaghetti may get heated at a different in a different way.
So, you are thinking both spaghetti and meatball in the same zone?
Yes.
Rather than, so under those circumstances, you may have to adjust the dielectric heating properties of either spaghetti or meatball, so that for a microwave they are seen as the same product.
Okay.
So, if the dielectric properties are much uniform, then microwave is going to seem as the same thing, and then it is going to heat to the same temperatures.
Okay, because that's the same principle they may apply for those packed lunches, right? Like the tray that is directly put in the microwave and it heats uniformly.
Right.
It heats uniformly.
Right. So, the TV dinners, they
Yeah.
have different platforms, right, like different packets. So, one may have rice, another may have a vegetable, another may have, so each has a different zone. So, that means you are not probably adjusting the salt anything, but you kind of control through your film. But there are multiple ways of achieving the same goal. You can also adjust the dielectric properties of some of the salt in rice, your vegetables and so on, but you can also do with packaging.
I have one basic question, that what are the major challenges which we are facing in using the microwave processing at industrial scale, and what could be the remedies?
Right. So, microwave technology for industrial applications is kind of slowly it came in only 2010, 2012. Now, I think the equipment providers are limited, right. So, it's a new technology, so probably at least 2 providers. Europe has more providers than US, so that's probably one limiting factor. Second, you probably have competing technologies, right. So, you probably have, at least in the US, more and more consumers are interested in what they call pasteurized products than shelf-stable products. So, microwave processing was initially developed as a sterilization tool, whereas I think the consumer interested in pasteurization, and right now that too with the clean label movement and all those things, the consumer want less heat processed samples. So, when they look at microwave, probably it's more heat processed. So again, there are industry want to prefer different methods than microwave processing. So those are all the complex things. But ultimately look at this as a tool. So there are products which are heat stable, microwave can be readily adapted. There are products which are heat sensitive, microwave may not be adapted.
Sir, so I want a suggestion from you that as a food process engineer, what are the what are the factors which we can tap in to grow the microwave technology more and to give a better feel to the industry or to the consumer that they can accept these technologies.
So I think like again, the technology adaptation is going to be a slow and nonlinear process, right? I think in other words, doesn't matter how much academic researchers provide information, the industry has many other factors to decide whether they want to use microwave, Omi heating or some other technology. So we probably, we can give them scientific knowledge, but it's up to the industry to choose which tool to use.
Yes.
So I think that's probably going to be different depending on whether you have a large manufacturer, small or medium sized manufacturer and so on.
Yes. Sir, would it depend on the customer preferences or the area wise that some as you mentioned that as the USA customer doesn't like this and they want the pasteurized product more. So it would be the factor that the consumer preference would be affecting the companies and the researchers also.
Right, sure. Because a lot of times the consumer drive the industrial adaptation of technologies because ultimately companies want to deliver products consumer like. So that means they may be choosing technologies based on some of those consumer preferences.
Sir, I have one basic question. In general, if we search the mainly what are the industry they are using microwaves, so we found that microwave dryer and microwave digester is getting more popular instead of microwave decontamination unit. What's your opinion, sir? Why the industry prefer instead of decontamination unit? I know that in case of microwave dryer, it can be very fast as compared to conventional techniques. So, what will be the most probable reason? So, because of that, these two domains are getting more importance rather than decontamination unit. And secondly, instead of like high like heat resistance microbes which can be easily deactivated using microbes, instead of that or whatever the technologies that we are mainly used, either it can be ohmic heating or pulse electric feed, they had their own limitation. So sir, what's your opinion for large scale purpose? So is there is a practical chance to getting absorbed by the industry, or there we need to find out another existing technology which can replace this innovative technologies?
Right. So let's kind of look at one thing at a time. So the first thing is microwave drying, commonly adapted in the industry. So if you probably broadly look at the different unit operations, drying is probably one of the most energy intensive processing applications. So conventional drying takes a lot of energy and so it's much higher energy intensive. So you have to find a way to reduce energy use in food process applications and so on. So in that sense, microwave is much more energy efficient and then it can also dry samples much faster compared to conventional drying, and then you may have a better quality. So that's where microwave drying, radio frequency drying, these are all getting more popular compared to the conventional drying methods. So I think that's probably one of the applications. So the second question is related to which one?
So sir, what will be the future of this decontamination unit? If we can really rely on microwave decontamination unit, or we want to find something more alternative technologies that can be replaced, which can be commercially viable?
Right, sure. So again, this is a moving target. So think about this as different tools, because one of the common um, challenge people do is, and again it's probably it's a human nature. So if I'm a researcher spending 10 years or 20 years in my life focusing on microwave, or I'm focusing on high pressure, or I'm focusing on UV, different technologies, I believe that technology is probably can do solve all the problems. But in reality, no one single technology can do everything for all wide range of food products. So you have to kind of look at this as a tool. So I have multiple tools as a industry person. I have microwave, I have UV, I have high pressure, pulse electric field. So for this application I may use this, for this application I may use this, but it's going to cost this much, this is going to cost this much. So I have this much budget available, then you choose the appropriate thing.
Is there any country to using this kind of multiple system, or any country industry is currently using this like combination of different technologies on a single unit, processing unit?
So like I think you probably may not use this combination. So there are two separate things. So for example, you may be processing potato soup, you may be using for example aseptic processing for potato soup line, whereas you may be drying some material, you may be using RF drying. So it's kind of more product based or category based, but remember the companies want to maybe have one single technology and then try to use as broad as possible. In that sense, today conventional heating process probably fits that because they can able to do wide range of products, but it has its own limitations in terms of energy efficiency, water use, sustainability, degradation of nutrients and so on. So it's kind of slow process. So other thing is the company is going to have invest in equipment which is legacy operation, is somebody is using it for 30 years, 40 years and the equipment working fine, there is no incentive for them to replace with the expensive unit. Whereas you are a new entrepreneur or new startup company, you want to invest, you rather invest in a new technology than conventional technology so that you try to get a competitive advantage. So I think those are the type of things you have to make. So it's not purely scientific, but a combination of science and then the business decision needs to come together.
Sir, last question. In 2000, most probably 2019, there was rumors like Japan is going to ban the microwave due to the irradiation. Sir, what's your opinion on large scale point of view? If we use the microwave in in industry, they are using the microwave for like one or two operator will be there to use this microwave. Technically speaking, it's not, theoretically it's not kind of leakage of the microwave radiation, but in practically there also be and certain some types of bricks that can be microwave can be processed for the worker to the. So what will be the safe limit or you can say safe distance to avoid this kind of like injury or irradiation problems?
Right. So as I mentioned in one of the slides, the FDA or the has certain leak test, and I think it's probably more around the prevention. So in other words, they don't want any leaks, so you can probably provide appropriate metal shields and things like that, so that there's no leak of microwave for the household operator as well as the industrial operator. So I think that's probably a simpler way, and you can probably measure the leaks and so on. But I'm not a safety expert for microwave, leak detection, all those things. So maybe you have to look at that appropriate guideline and then make that determination. But normally, as long as you use the appropriate controls, shields, and so on, microwave operation is safe to use.
Okay, thank you, sir.
Sir, as you said that in the discussion that conventional technologies are in the product, if we are going with the product. Conventional technologies are applicable, but if we are going microwave heating, ohmic heating, they have the specific limitations with the product also. So sir, we can say that this is the main challenge or one of the key challenges that these technologies are not being adopted by the industries.
Can you repeat the question again?
Sir, as you have said that ohmic heating and microwave heating, they have the product specific limitations. But in comparison, the older technology or conventional technologies, they have the limitations such as the environmental barrier or pollution barrier. So we can say that this is giving an opportunity to the entire industries that they are not going to use the new technology.
So again, like a lot of the adaptation of new technology, at least I'm talking in the US, it's driven by the consumers.
Okay.
So if consumers not worried about the health and wellness and additive pre-processing and so on, the industry may not have interest in looking at, for example, non-thermal technologies and so on. Whereas with the interest in minimally processing, clean label processing and so on, the high pressure pulse electric field and many of these technologies came in. They were more expensive compared to conventional processes, but you make a product with the less expensive, no consumer is buying, or you make a product, consumer willing to pay more, which one you choose. So usually, like for example, many companies like guacamole, juices and so on, the consumer is willing to pay a little bit more premium for some other products if they think they are getting the appropriate quality. So for example, in juice products, consumers think it has a better nutrition retention. Whether or not actually there, I think it's a little bit marketing, the scientific data is still evolving. That needs to happen in the future. But at the moment, I think that kind of helps the industry to adapt some of the new technologies.
Yes, there is a psychology behind it that if they are getting it cheaper, they would not believe on the nutritional quality and they will prefer the costlier one. Sir, so, but we can do this for the countries like, sir, we have countries where food nutrition is necessary, like African countries, but we are not able to provide them. And we are today in the world, if we are trying to focus on the sustainability, so we can use this product there also.
So again, food is something each set of consumers going to have different preference, right? So for example, you have US consumers prefer certain type of meals or food products. Indian consumer prefer different, whereas European consumers prefer and so on. So you have to adapt that for your local customer needs and then try to formulate that. So for example, in a different topic, if McDonald's come to US or India, they are not going to sell the same product in the US versus in India. They are going to localize and adapt the local products for the Indian market and so on. So I think that's where you have to consider that. And it's probably difficult for one country to make products and sell to different countries, unless it's a very standard product. So for example, milk.
Yes.
So milk may be common, so whether it's done in the India or US or Europe, probably you can export to different places, assuming you can able to meet the shelf life.
Okay, sir. Thank you, sir.